All right, let's look at the limit comparison test. Related to the direct comparison test, it's similar in that I need to have an and bn be positive. But this time, I look at a limit. I want the limit of an over bn to exist and is not 0 or infinity. So the limit has to exist and be a number between 0 and infinity. So if that's the case, then the sum an and the sum bn both converge or both diverge. So these sums do the same thing. They either both converge or they both diverge. Let's see an example. So what about the sum n going from 10 to infinity of 1 over n squared minus n? So to use the limit comparison test, I'm going to say that these are my an terms, and I'd like to compare this series, this sum, with another one. Now, here's how to get intuition about how to select the second sum. I'm going to compare by deciding that the term in this circled region that really affects the behavior is n squared. So n squared dwarfs n for large values of n. So the most important term on the bottom is definitely n squared. So I'm going to compare with the sum 1 over n squared. So I'm going to drop the n term, deciding that really the n squared is what matters. So this is my bn. And I know that this converges. It's a convergent p-series with p equals 2. Okay, so we see that the limit as n goes to infinity. So I'm going to take my an, 1 over n squared minus n, and divide by bn, 1 over n squared. So I don't like fractions within fractions. Let me simplify that. I think if you simplify, you'll get n squared over n squared minus n. Now, this is a polynomial divided by a polynomial. Only the first terms affect the behavior of this fraction. So the limit is actually 1. 1n squared over 1n squared, the n term insignificant. So the limit is 1. 1 is not 0, and 1 is not infinity. So that means both of these series do the same thing. They both converge. They both converge because I knew this one was a convergent p-series with p equals 2, so that means this one also has to converge. All right, let's do another example. What about the sum n going from 0 to infinity of 4 to the n power plus n over 3 to the n power minus n? Now, I'm going to compare with the sum 4 to the n divided by 3 to the n. For large n, 4 to the n is much more powerful than puny old n. So the term that matters on top is 4 to the n, and similarly, the term that really affects things on the bottom, 3 to the n. So I'm going to see what happens if I compare with this. So we see the limit n goes to infinity. So this would be my an here, and this would be my bn. So I'm going to take this 4n plus 1 over 3 to the n minus n, and I'm going to divide by this term. So when you divide, you flip and multiply. 3n over 4n. So this is the limit as n goes to infinity. I think I would get 12 to the n plus 3 to the n times n over 12 to the n minus 4 to the n. Now, 12 to the n grows much more rapidly than 3 to the n times n. I could tell that this limit is going to be 1. Again, because the most significant term on top is 12 to the n, the most significant term on bottom, 12 to the n. Now, if you don't like that, if you don't have the intuition, you could always use L'Hopital's rule or something to take the derivative here. But in this case, I kind of knew the answer was 1. That means both of these series do the same thing. This series diverges. I could tell it's a geometric series. It's a geometric series with the value being 4 over 3, larger than 1. So both diverge. Okay, so that's the limit comparison test. But I'd like to show you why this is actually true. It's not that complicated of a reason. So why does this work? Well, if the limit exists, then eventually the values an over bn have to be in between two positive numbers. So the limit is going to exist. It's not going to be 0. It's not going to be infinity. It might be like a number 1. So what I'm saying is, eventually, the terms in my series are going to be in between two values for all n. Here, let me try to draw you a picture of the situation. So I've got my terms in my sequence here. Like this is the n axis. Let me try to like graphically depict what an over bn might look like. So it might go, like this in the beginning, but eventually, since the limit exists, this would be like the limit here. The terms that I'm trying to depict are the terms in the sequence an over bn. The limit exists, so eventually the terms in this sequence have to land in between little m and big M. Both of these positive. So my whole sequence, lands in here. Well, then eventually, for large enough values of n, what this says is m times bn is less than an, which is less than capital M bn. So I just multiplied everything through by bn. So what happens is, if I add up all the terms, eventually, for large enough values of n, the sum bn is going to be less than the sum an, which is less than m times the sum of bn. Now we just use direct comparison test. If the an series converges, so if this middle sum is finite, then the smaller sum also has to be finite. On the other hand, if this middle sum is divergent, if this adds up to arbitrarily large numbers, then the larger sum also has to be divergent. That's the direct comparison test. So the limit comparison test is secretly a direct comparison test. However, I think the limit comparison test is usually a little bit easier to apply in practice. Again, the trickiest part in doing a limit comparison test is deciding what to compare with what. The reasoning that I gave for these problems was to decide which terms were really important and which terms could be neglected, which terms could be kind of abandoned. Then I compared to an easier series where I kind of erased the terms I didn't need. I did that in both examples. All right, excellent.